Hi everyone, welcome to this video in which I'm going to explain you how to install components and libraries to the LTspice computer simulation program, and also we will perform simple digital simulations. Okay, so let's start. First of all, let's take a look to the components that we have in LTspice. We can see here that we have different libraries and different components. All of them are located in this directory here, in this folder. Okay, users, Alonso, documents, LTspice 17, lib, and sim. Sorry. Okay, so let's take a look to this folder. So if we go to documents, then LTspice 17, then libraries, okay, and then we have here two important folders, which are the sim folder and the sub folder. Okay, in sim folder we have all the symbols for our different components. So these files here, what they have is the graphic description of each component. For example, if I open this one, 4053, then we can see here that what we have is the drawing of our component, which is digital switch, okay, with two terminals, okay, and one common pin here, and then this is the control voltage. So at the end, these files .asy, they have the drawing of each component. Okay, same thing in these other folders. These are complete libraries. For example, if we enter here in 74HC, we can see all the drawings for the different components. For example, 74HC00, this is an AND gate. Okay, so we have here the drawing corresponding to the NAND gate, okay, and so on. For each component, we need also another file that we are going to place here in a subdirectory. And for this, we have two possibilities. One possibility is to have a description in text of our component. So, for example, here for the same component, the digital switch, we have the 4053 here. If we open this with Notepad, then we can see all the description of our component. Okay, we will see how to do these components in a future video. Okay, so we have here the description. At the end is a sub-circuit with a name, different inputs, different parameters, and this is the description of our components, our switch. Okay, and this to indicate that we are ending the description. Okay, and then the other possibility when we have many components is to have a binary description, which is here. For example, for the 74HC family, we have a complete library. So all of them, all the descriptions are inside this library. This is a binary file, and we cannot see what we have inside right now with Notepad, for example, okay, because it is binary. This is the other way to implement a library in LTspice. Okay, so if we go, for example, here in downloads, I have both the drawing for this component and also the description of the operation of the component. So in order to install this component, what we only have to do is to take the sub-circuit, this file, and copy it in the corresponding directory. And also take this other file, the drawing and copy it in the corresponding directory. It's as easy as that. Okay, so we just have to take these files and go to, again, documents, LTspice, libraries, copy the symbol here. So we have, for example, already this component here, and then copy the description here, 4053, in order to have also the behavior of the components. Okay, and then, for example, if we want to install a complete library like the 74HC, then we can have a folder like this one, in which we are going to have the description library 74hc.lib, okay? And then we have this other folder, in this case compressed folder, so we can enter here, and then we can see all the symbols in this compressed folder. Okay, so we only have to copy this library, okay, and all this folder in the corresponding library folders that we have seen before. In documents, LTspice library. Then in symbol, we copy the complete folder 74HC with all the symbols, descriptions. Okay, and then in the subcircuit folder, we copy the library 74hc.lib. Okay, so then we have everything. So right now, if we go to our LTspice circuit, we can see after this, and we need to close the program and start it again in order to refresh these installations. So we can see now that we can see this folder 74HC with all the components. Okay. In this library, we have the different components in two types of drawing, with this typical drawing, and then with this other drawing corresponding to the DIN standard. Okay, but at the end is the same thing. All of them are represented in both ways. And then for the switch, we can see that we have installed it in the main directory of the library directory of LTspice. So we have it here, the 4053. Okay. So this is this is how we install the different components, and you can see that it is very easy to do it. Okay. Where can we find more information about these components and find also libraries and new components and so on? One place to do that is the LTspice Yahoo group. Okay, if we search for LTspice Yahoo group, then we will find this link here. Okay, entering in this link, then we can see all the information regarding to this group. Okay, you have to register in this group. It is free. So just giving your email address and a password, and then you can access to all the information. So here, for example, you can see the different posts, asking questions, answering questions, and so on. Also, we have here the files. Okay, so in these files we can find different components and different materials, okay, for different applications. Okay, so this is quite interesting. okay, with a lot of information regarding LTspice. And now in this video we are going to see how to perform very basic digital simulations. Okay, so for example, let's do a combinational circuit, simple circuit using, for example, 74HC and using NAND gates. So it's just to place our different gates to implement our circuit. Okay, we can do a zoom and move a little bit everything. Okay, so now we can do the wiring, just pressing here, as I explained you in the first video. So we can do the different connections, something like this. Say for example that this is going to be here connected, and this will be connected here, and then something like this. Okay, and then our inputs, for example this one, and this will be connected with this other, and then another input, and then maybe we can do something like this, and then we can have another input here, and this will be connected to this input also. Okay, so we have a circuit with 3 digital inputs and 1 output. Okay, so these are in principle TTL compatible gates, so they will be operating at 5 volts. We can right click on any gate and see more information about the different parameters. They are going to be supplied at 5 volts, and they are directly supplied at this voltage level, so we don't need to add a voltage source to supply the gates. Okay, but we need to add a voltage source in order to implement the inputs. Okay, so let's go here, components, go to the main directory, and then select voltage, and this will be our voltage source in order to get the 5 volts for the inputs. Okay, so we need also a ground here, and then place the wires. I recommend to do something like this. Okay, and then selecting the voltage source, we give 5 volts, for example, for the voltage source. Okay, and then we will give here a label. We will put here a label, say for example label 1. So anything with any net with label equal to 1 is going to be connected to 5 volts. Okay, so if we want, for example, to include here a combination like say 1, and then sorry, 0. Okay, then we have this combination in our circuit, digital circuit 1, 1, 0. You have seen that when I select 0 for a label, it automatically draws it as a ground symbol. Okay, so we have 1, 1, 0. So now we can do the simulation. In this case, in this simple circuit, we can do a simulation like a simulation at a steady state, so we can use the operating point simulation. Okay, so we can go to simulate, edit simulation command, and then select here the DC operating point. Okay, so we select this simulation mode. Okay, and this is all. Right now we can perform our simulation. Okay, there is a mistake here. There is an error here. Is indicated that the program doesn't recognize these gates 74HC00, because when we use library that it is not included in the original distribution of the program, we need to include a directive in order to instruct the program to find the new library. Okay, so we need to write here .inc 74HC, which is our library, hc.lib. Okay, so with this sorry, there's a mistake here, .lib. So with this directive, we are instructing the program to use this library in our simulation. Okay, so right now, if I run, then it will be running okay. Okay, so we can see the results here. Okay, in all the nets. This is not very easy to understand. Even we can see the zone currents inside the different gates and the different sub-circuits, but this is not very interesting for us right now. Okay, so there is another possibility of seeing the results, which is very easy. Is just to go to the output wire, for example, and click left click on it, and then we'll see the voltage that we are going to have in this wire, and we can see the voltage on any net. Okay, just by clicking on it. Okay, so we see that this is 49999, which is 5. Okay, 5 volts. So this is represents a high level for the digital signal. Okay, so it's equal to 1. Okay, and then we can select other inputs, for example 100, and then perform the simulation. Okay, and we will see again the results in all the nets, and then 5 volts in this case at the input. Okay, same thing, for example, for the combination 000, then we will get again the results. Okay, and with this we can test all the different combinations. Okay, there are other possibilities of doing this using, for example, several pulse waveform here, voltage sources with a pulse waveform. Then we can go and simulate with a transient simulation all the possibilities. Okay, this is just a first example on how simulate to simulate any simple digital circuit. Okay, we will see now a little bit more complicated example. We are going to delete, for example, this part and this part and this, and we are going to simulate, for example, a RS flip-flop. Okay, so for this we will use 2 NOR gates. Okay, 2 NOR gates like this. Okay, and then we will connect it to implement our RS flip-flop. Okay, this will be the output, and we know that this input goes to this output. You see that I cannot draw out of orthogonal mode now. Usually, if we want to make it more professional, then we can draw the wire with a slope, which is better for this drawing. For this, we can go here, I think, Tools, Control Panel, and then go to Drafting Options, okay, and then select orthogonal snap wires, okay, and select this orthogonal snap wires, okay, and then I should be able, okay, sorry, I need to go first to drawing mode, okay, so with this I can draw the wire with a slope so we can see it a little better, okay. And then we will place a label for our inputs. In this case, we have reset here, and we have the set here. I can place the reset and then edit the label to set. Okay, so this will be the reset, and this will be the set of our flip-flop. And then with another label, the output, okay. And then in this case, to simulate this, we are going to use pulse waveform for the inputs, okay. So we are going to connect this one, for example, here to the reset input, but now we have to change this in order to be a pulse waveform voltage source, okay. So we can right click here and go to advanced, okay. We press this button here, advanced, and then we can select the pulse waveform, okay. And then we have all these parameters here for our pulse waveform, okay. The initial voltage, for example, is going to be 0. The on voltage is going to be 5, okay. So this is the two voltage, these are the two voltage levels for our waveform, for our pulse, 0 and 5. The delay is if we want to start the waveform not at time 0, but a little bit later. Okay, in this case, we are going to start directly from 0, so we select here 0. Then we have rise time and fall time. Okay, these are the times that it is going to take for the waveform to go from 0 to 5 volts rise time and from 5 volts to 0 fall time. Okay, so we are going to use here 1 kilohertz waveforms, so we can select, for example, for the rise time 1 micro. It is accurate enough, and for the fall time also 1 micro. Okay, and then the on time, we want to have 1 kilohertz, and we are going to use an on time of half the period, so this will be 0.5 millisecond and period 1 millisecond. Okay, and the number of cycles, this is if we want to generate only, say, for example, 3 periods, 4 periods, or 10 periods, whatever, and then stop the waveform after this number of periods. Okay, if we don't use this parameter, then the waveform is going to be generated forever. Okay, so we leave this blank. Okay, and then we have this waveform. And then for the set, we are going to select to implement a similar pulse voltage source. Okay, we can simplify by copying this, okay, and then connect it here. Okay, and now in order to avoid that both voltages are going to be exactly the same, we are going to include here, or better selecting here with right click, then we are going to implement a delay in this waveform. So it is not going to start at the same instant like the other one, V1, but we are going to delay this waveform in, say, for example, a quarter of period. So 0.25 milliseconds. Okay. So, okay, and see what happens in our circuit with this. We can remove now this label, this other label, because we can only have one label for each net. And I think that now everything is ready. We only have to select the simulation command that we want. In this case, with edit simulation command, then we select transient simulation, and we will select for the stop time, say that we are going to see, for example, 3 pulses. So this will be 3 milliseconds. And in my experience, it is better to skip the initial operating point solution in this kind of digital simulation, because at the end it's not very relevant. So we can skip this, and this is going to make our simulation quicker. Okay, so, okay, and then we place the directive here. For example, we have the transient until 3 milliseconds, and avoiding the obtaining of the initial of the operating point. Okay, so now press run and we'll see what happens. Okay, so we have our circuit at the bottom and the results at the top. So we are going to include 3 different panes, 2 for the inputs and 1 for the output. Okay, so select here, add plot pane and another plot pane. Okay, and then here at the top I'm going to select the reset. Okay, so select this window, and then with the scope press here, so we can see here our B reset. Okay, so this is the waveform that we are including for the reset. Okay, and then same thing for the set. Okay, but I want to draw the set on the middle pane, so I'm going to remove it from here, delete this state. I have to select first this pane by clicking on it, and then going back to our drawing and select set, and then we can see the waveform is the same square waveform, but now with a delay of 25 milliseconds. Okay, and then now we can select the output. Sorry, again, I want to see that in the other pane, so select this bottom pane and then go to the drawing, select output, and we can see here our output in red. So now let's analyze if everything is okay. Here in the first interval we are selecting reset to 1 and set 0, and the output is 0 because we are doing a reset of our flip-flop. Okay, and then here we have 1 for the reset, 1 for the set, and 0 for the output. This is all because for this flip-flop, as we know, this flip-flop gives priority to the low level at the output, to 0 at the output. Okay, so when we make an input of 1 1 in reset and set, the output is going to be equal to 0. Okay, it's another possibility to write a 0 at the output. Then in this other interval we have reset 0 and set 1, so we are doing a set. Okay, so the output is equal to 1. Then we have 0 0 in reset and set, so this is the memory state of the flip-flop, so it remains at 1. Okay, so then 1 0 is reset, so 0 again, 1 1 is a reset, and so on. Okay, so we can see that it is operating correctly. Okay, so we can see it a little bit better, an image of the results, and here for you to see better the circuit with all the definitions on directives. Okay, remember always when we are including new components and libraries to include this directive to instruct the program to use this library for our components. Okay. Okay, this is all for this presentation today. I hope that this has been useful for you, and we will see in our next video. Okay, thank you very much and goodbye.